Hi, we'll present our work Precision and Recall on imbalanced test data. I'm Hongwei. This is a joint work with Jean-Marc, Costas, and Changsang while working at Yahoo Research. Here is the motivation for our work. We have deployed multiple binary email classifiers to production. After deploying these classifiers, we'd like to monitor these classifiers' quality regularly. In order to do so, we need to sample emails periodically and compute metrics like precision and recall on the sampled data. And several classifiers are heavily imbalanced. Table 1 shows a mocked example of an existing monitoring test for a binary classifier based on random sampling. 5,000 emails were randomly sampled from the entire population, and the confusion matrix was generated after obtaining the true labels from human editors and the predictions from the classifier. Out of the 5,000 emails, 4,732 are true negatives, showing this class is imbalanced. For this random sample, the margin of error of the estimated precision and recall is 5.3% and 6.2%, which does not satisfy our 5% margin of error constraints. The sample data is expensive to generate because it requires manually labeling by human editors, and we also need to do this periodically. So our motivation is to minimize the number of sampled data and the labeling while obtaining reliable confidence intervals for precision and recall. So this work presents a practical sampling strategy and a complete analysis for the confidence of precision and recall metrics of a binary classifier for imbalanced data. We first formulate the problem. We consider the simple binary classification setting where each data point has a true label and a predicted value in 1 as positive, 0 as negative. Our goal is to estimate the precision and recall of the population by sampling a test set. We use a confusion matrix C shown in Table 2 to summarize the test data, which reports the number of true positive, false negative, and true negatives. We also use pi, precision and pi recall, to denote the true precision and recall, and pi hat to denote the sample estimates. Eta denotes the confidence level, and z eta is the percentile point of standard normal distribution. The simplest monitoring test set would sample data from the whole population randomly and compute the precision and recall from the confusion matrix. Under the random sampling scenario, 4 cells in the confusion matrix naturally follow a multinomial distribution. Marginals and conditionals of a multinomial distribution follow binomial distribution. So the confidence intervals of estimated precision and recall have these forms. Note that when the data is very imbalanced, the number of predicted positive data is much smaller than the total sample size, making the width of the confidence intervals very wide, especially for precision. To mitigate the class imbalanced issue, the intuitive solution is to oversample the positive data. Then we oversample by taking random samples from 2 groups. One is predicted positive group and a predicted negative group, respectively. They are denoted by the 2 green rectangles in this figure 1. This corresponds to 2 independent binomial distributions in the confusion matrix, rather than a multinomial distribution under random sampling strategy. With oversampling, estimated recall needs to be adjusted by oversampling ratio, denoted by S. Also, we use imbalance ratio K, the ratio of predicted positive data size to predicted negative data size, to denote how imbalanced the data is. Then by the normal approximation, we can derive confidence intervals for precision recall in its oversampling setting. A Bayesian approach can also be applied to estimate the credible intervals for precision recall for a future post-deployment monitoring test. Given the prior knowledge and the observed pre-launch confusion matrix for the classifier, we can predict the estimated precision and recall of future independent monitoring test samples. At the beginning page, we showed a mocked example with the confusion matrix on 5,000 random sampled emails. Now we come back to this example and would like to analyze how oversampling will affect the precision recall's confidence intervals using the same sample size, 5,000. This figure shows the plots of width for confidence or credible intervals. X-axis represents oversampling ratio. Y-axis represents confidence intervals width for precision at the left figure and recall for the right figure. Here, the confidence intervals are denoted in black color, and the Bayesian credible intervals with different values, W is 5, 10, 100, represent different variances. For precision, on the left side, the width for both confidence interval and the credible interval are always getting smaller and smaller as the oversampling ratio increases. For recall, on the right side of the figure, the width for both confidence interval and the credible interval decrease first until the oversampling ratio S approaches to a certain point, and then they slowly increase as S continues to increase. We also see the larger the variance W gets, the closer the Bayesian curve gets to the frequentist curve, denoted by the black plots. From the figure, we also see with oversampling, it is easy to satisfy 5% margin of error using 5,000 samples, which cannot be done by random sampling the 5,000 samples. From the plots, we see precision variance is always smaller with large oversampling ratio. But for recall, the variance reaches a minimum at an optimal oversampling ratio. Because recall is decided by a function of the ratio of true positive to false negative, the estimated recall's variance is decided by the trade-off of these two factors. There is a sweet spot to minimize the uncertainty of the recall estimates. In both frequentist and Bayesian view, we can analytically find the optimal oversampling ratio to minimize recall's variance. And this optimal oversampling ratio is decided by the imbalance ratio K and estimated precision and recall. Next, we present our experiment study. We use simulated data to assess our analytical method's ability to construct accurate confidence or credible intervals against the simulation methods, including Bootstrap and Monte Carlos. The parameters of the experiment are the imbalance ratio K for classifier prediction, and the true precision and the recall of the classifier over the population data, the sample size V, and the oversampling ratio S. For each combination of these parameters, we generate 1,000 samples. And the Bootstrap size and the Monte Carlo size is also 1,000. So given a combination of all these parameters, we can compute the approximate coverage probability. Here, both bootstrap and Monte Carlo methods are used to obtain the precision and recall confidence interval and the credible interval respectively. So bootstrap, the sample is an estimate of the population, and an estimate of the sampling distribution can be obtained by drawing samples with replacement from the observed sample and the computing statistics in each new sample. But for Monte Carlo, the simulation refers to repeatedly creating random data from the population and computing statistics from each random sample. For comparison between the analytical methods versus simulation methods, the analytical derivation of confidence and the credible intervals is complex and needs normal approximation, while using a simulation process to estimate the distribution is easy and accurate. Yet, the superiority of analytical method is that we can have explicit forms and correspondingly derive the optimal oversampling ratio for recall, which cannot be computed through simulation process. So this page and the next page is they show the experimental results for frequencies approach and the Bayesian approach. Both these two tables show the coverage probabilities for precision and recall at various parameter combinations. Coverage probability gives the proportion of times the true precision and recall was in the interval. We see that overall, the confidence and the credible intervals hold their levels reasonably well for all four methods, since most coverage probabilities are close to the expected value, 95%. Next is the application. We have some highly imbalanced classifiers deployed in Yahoo Mail production. After deployment, we wish to monitor the quality of those models at regular intervals. And given a limited budget for monitoring, the question becomes how big of a sample we should get and whether we should oversample the small class or not. We will estimate the minimum number of samples needed for each classifier and to reach a desired confidence interval width, given a reasonable estimate of precision recall and the imbalance ratio K. So below, we show two classifiers. For each classifier, we plot the relationship between the oversampling ratio S and the width of the confidence intervals for both precision and recall by fixing the sample size. For the classifier on the left side, the imbalance ratio is 1/30, and we chose 1.5 as the oversampling ratio. For the classifier on the right side, the imbalance ratio is 1/2. We do not need to do any oversampling for this classifier to satisfy the business needs. At last, we conclude. The confidence interval for precision is always getting better with more oversampling. By oversampling, we obtain more data for the positive set, so it becomes more confident about the precision. For recall, the confidence interval's width reaches its minimum at an optimal oversampling ratio, then starts increasing as S gets bigger. However, the slope of the graph increases very slowly. The more imbalanced the data, the flatter the slope. So in generally, it is a good idea to oversample positive data since the precision can benefit a lot while hurting recall very little. We also would like to emphasize that our work focuses on saving the labeling cost of test data rather than training data. In many settings, it is required to constantly monitor a previously trained classifier by evaluating the latest batch of data due to the potential data drift, and this can hurt the classifier's performance. Our work will be very useful in these settings. Thank you.